Hi, I'm Justin, and I'll give you a brief rundown on our poster detailing a countermeasure for detector manipulation attacks. For more details on the paper, you can check out our paper via the QR code provided on this slide, as well as on the poster. The main takeaways from this are as follows. When we perform QKD, there's a need to mitigate a class of detector manipulation attacks, notably including the blinding and the fixed state attack. There already exists a wide variety of existing countermeasures. This includes monitoring detector photocurrents, using a watchdog detector, changing the detector operating characteristics, among others. And here we propose a countermeasure that only requires a loosely coupled LED and perhaps a bandpass filter to prevent light leakage to perform our own detector manipulation detection. And this is easy to implement and retrofit on existing systems. So I'd like to give a quick introduction on the blinding and fixed state attack before we actually talk about the countermeasure itself. Okay, the detection events by an APD is distributed according to the statistics of input light. Okay, for our demonstration, we use a Bosonian source of light with an event rate of roughly 50,000 events per second. And this corresponds to roughly one event every 20 microseconds. In a blinding attack, a possible attacker, say Eve, can inject bright constant light into the system, and this shifts the APD away from the breakdown operating point and makes it no longer sensitive to single photons. Eve can then intercept the photons and generate single light pulses that deterministically trigger the APD corresponding to Eve's measurements. And this perfectly replicates the same photon counting statistics, but now Eve also has the same measurement results as the legitimate receiving party. What's notable is that the power levels used for blinding and the fixed state attacks are much higher than that of single photons. And you can rely on this fact to introduce blinding scenarios to our own detectors by use of a retrofitted LED loosely coupled into the detector. The interference filter in our setup is there to avoid leakage of light to Eve. Any detection event that falls within this self-testing period when we switch on our LED can then be subsequently discarded during event post-processing by correlating with the electrical pulses that are sent to the LED. There are a couple of countermeasure strategies that we can undertake with this hardware setup. Firstly, we can rely on the fact that single photons are no longer detected when the detector itself is blinded, so any addition of low light cannot be detected. In this scenario, we can sort the detector with low light such that the average photo detection events is slightly larger than that during normal operation, indicating that it is not blinded. Secondly, we can also rely on the fact that only very bright light levels on the order of microwatts and above can be used to trigger a detection event in a blinded detector. And in this particular scenario, we send in short pulses of light strong enough to deterministically trigger a detection event in an unblinded detector, but weak enough that it has zero probability of triggering a detection in a blinded detector. And in our particular setup, this manifests as a correlated detection within 60 nanoseconds upon pulse trigger to the LED. Lastly, and thirdly, if we proceed to self-blind our own detectors with bright light, then no detection events will also be observed unless there are bright fixed state pulses that are being sent in. This has the beauty of actually detecting the fixed state pulses that are being received. And similarly to the previous strategy, the high power also ensures the near unit probability of detecting a single photo detection event right after a pulse trigger. These three strategies essentially concludes the main gist of the poster, which I would recommend checking out using the QR code provided earlier. The paper itself will furnish the relevant experimental details for those interested. The simplicity of implementing this countermeasure, as well as the ability to quickly retrofit detectors in existing QKD systems to mitigate this class of attacks, makes this a particularly versatile technique. Thank you.